In this video, we're going to talk about very basic statistical analysis, especially in conjunction with the project Lead the Way for Principles of Engineering. So as we are going forward, the things that you want to look for and should be able to calculate are the mean, the median, the mode, the range, two different types of standard deviation, and kind of recognize what a histogram is and what it tells you about your sample size. So as we're going through this, these are the big things that you should definitely have down in your notes, because it's going to help us with our M&M activity and how to calculate certain things within that section. So let's talk about the very first one, and these are all relatively simple. I'm sure you guys have messed with them before in your math classes, but we just want to go over those really briefly so that everyone is on the same page and you have a way to come back and look at what the stuff might mean if it slips your mind. So the first thing that we're going to talk about is the mean, and another way we say that is the average. You guys are super familiar with this. So the mean is if you add up all of the values within your sample and divide it by the number of values you have, that's going to give you your mean or your average. So think about in school, sometimes classes will take the average of all of your tests or all of your quizzes or something like that. So the idea is you're taking all of those values added up together and dividing them by the number of those values. Now, the thing about mean that we need to watch out for, and we'll have an example about this, is if you have outliers, you are going to have a big change in your mean or your average, which means it may not represent exactly what you are looking for. So, for example, if you are doing solid in a class and you're pumping out 85s, 90s, something like that, and then all of a sudden one test you get a 0%, that is a monstrous deficit to kind of the points that you earn in that learning and might not represent exactly what you know. So another way, or kind of to calculate the mean value, is taking all of those numbers added up and divide it by the number of values. So I would grab my handy dandy calculator. I would take 48 plus 63 plus 62 plus 49, blah, 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 blah. I would add all of those up and I would divide them by the number of values we have. So I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which would give us our overall value. The mean would be 47.64. Not too shabby. You guys have seen this before. Now, a different idea is the median. And again, we'll talk about what the difference between those two might be. But the median is if you were to line up all of your data and split them into two equal groups, that may give you a better idea as to what that kind of the middle ground is for all of your data. So what you're going to have to do is you're going to have to take all of those data values and you're going to order them from lowest to highest, which may take a little bit of time. But what's really, really nice for this is if your data is skewed to the right or to the left, or if you have really big outliers, like a 0 in the grade book, or a really, really big value if you were taking data down, it's kind of nice to see that median value to get a better idea as to what's going on. So if I were to take the median value of our data set that we have right here, the first thing I'm going to do is I'm going to order it from smallest to largest, and I'm going to use my fancy-pantsy PowerPoint magic to do that. So notice our lowest is 2, our highest is 63, and I just line all of them up. To find the median value, you want to find the point that splits the data set evenly. So if I go, we have what, 11 here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I would pick the value that ends up in the middle of the data set. So it would be what, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that 58, that is the value that splits our data set in half. So my median is 58. And so that gives us a little bit of a different idea as to kind of what that middle point is. Now, we had 11 in our data set, which is a nice odd number, which means there is one number that is precisely in the middle of that. if we have a data set that has an even number of values, so if I look at this, I say we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What I would do is I would find kind of that middle spot. 1, 2, 3, 4. So my middle spot is in between 58 and 59. And I would find the middle spot between those two. So if I were to add those up and divide it by 2, my median would be 58.5. So I'm trying to find what would the middle point between the middle numbers be if we had an even number. Even though they might seem really similar, it's very important for us to make a distinction between mean and median, because depending on the use, you may have a very different outcome. So let's say that you are a school district and you're trying to get teachers to come to your district. And so what we can do is we can just look at starting salaries, trying to get some of those young college kids ready to go. So what I've done is I have created a kind of each state's average starting salary for teachers. And just for kicks and giggles, I tossed in the starting salary for LeBron James back in the day when he was 19, came out of high school. So these are all starting salaries, all good numbers, but we're going to talk about mean and median and what that might represent. So what I would like you to do is, given the data set provided, I want you to do two things. Number one, calculate the mean for the starting salary, and number two, I want you to calculate the median value for starting salaries and really think about, if you are a teacher, which one looks better and which one kind of distorts the truth. So think about, if you're trying to get new teachers to come into your school district, and you put up a sign that says this: hey, your average starting salary for new employees is $746,000. That's pretty dang good. I would be in. But notice how it kind of obscures the truth. Obviously, the situation is bogus to start with, but in this case, the median is probably a slightly more accurate representation of what a starting salary for this person might be, because there are significant outliers in the data. Now, if all of the data points are relatively close together, your mean and your median are probably going to be very similar, but outliers have a big change or a big impact on how you analyze that data. So we've talked about mean, we've talked about median. Now let's talk about mode. And the mode is the most frequently response within your data set. And if we were to make kind of a frequency graph, and we'll talk about what that looks like in a histogram, usually that is the highest point of the curve. And we'll talk about what modal, bimodal, and multimodal might represent. So let's say we have our data set that we originally were working with. To determine the mode, all we have to do is look for that value that is repeated the most. And as I look at everything, it looks like 63 is really the only one that is repeated inside of there. So the mode of my data set would be 63. Now, you may have data sets that don't fit kind of that classic bell curve. Maybe you have a couple of humps inside of your data. So we could do what we call bimodal in picking 2 points that are represented there. So if I take a different data set, I have two 59s in there. It is bimodal because we have two different things that have the same amount of frequency. And we could do the same thing for if we had even more repetition there. So you can have data sets that have 1 mode, 2 mode, 3 mode, more than that, and it just kind of represents higher frequency values within your data set. Next up is our range, and this one is pretty easy. So you're just trying to see how many values are between your highest and your lowest. And standard deviation, this is going to be a fat old calculation, is the kind of the variance. How much is that changing? So if we're talking about the range, pretty simply, you're just taking your highest value minus your lowest value, and that tells you how many values you have in between. So if we organize our array like we did for the median, from lowest to highest. My lowest is 2. My highest is 63. In order to find how many points are inside of that range, I just take 63 minus 2 is 61. So my range within my data set is 61. Not too shabby. Now here is the big fat calculation, and that is standard deviation. And you are going to see this a lot, especially if you go into a science degree in college. You're going to be doing this all of the time. Now, Excel documents, and I believe sheet documents can do standard deviation for you. We're going to talk about where that comes from and how do you know the difference between sample and population standard deviation? Because in reality, we can really only do sample standard deviation because it assumes that there is a bigger group out there. So let's say you are trying to do a sample standard deviation of all people everywhere. Unless you can get every single person on the planet in your data set, you're just going to be looking at a sample with the idea that the more samples that you can collect, it's going to get closer and closer and closer to what the actual value is for the population. Now, if you have every single data point for something, so let's say you're able to get data on every single person in the world, then you can use population standard deviation. So when we say a parameter versus a statistic, a parameter is, you know, that number is absolutely everybody, rather than a statistic is just a chunk of that group. Can you extrapolate that out to represent what the entire population might look at? So in reality, sample standard deviations are really the only one we can use necessarily. Population is when we are looking at every single thing within a population. But they are very, very similar, even though their symbols are a little bit different. We can play with it just a little bit. So this is a very long process if you are doing this pencil and paper. So what I highly recommend is if you have Excel, just use the functions in Excel. And if you need some help with that, remember there's a ton of videos that we can use to figure out what that is, or how to select the right values for that. But if you did have to calculate this by hand, this is what everything represents. So your X with the line over it, excuse me, represents the mean, which we've already talked about calculating. Your X is the value that you're looking at within your data set. N is the number of values in your set, and then obviously the little sigma up there is you're kind of summing everything up. So there's 5 steps to this process. Number 1 is calculate the mean of all of your values, and I'll show you what that looks like in just a second. You're going to take the value in your data set minus the mean for every single value. You're going to square it, and you're going to add all of those together. Then you are going to take the number of values minus 1 and divide your summation by that value. And then last but not least, you're going to take the square root of all that stuff. So let me show you what this looks like. And if you need to, you can pause it. You can slow this down to see what's going on. So let's take our data set that we've been messing with a little bit. And I've organized it from smallest to biggest. You don't really need that for standard deviation. But step number 1 is I need to find my mean value. So I'm going to take all of those values, I'm going to add them up, and I'm going to divide it by 11, which is exactly what we've done before. So I know my mean is 47.64. So I'm going to put that on the back burner, make sure I can use that in a little bit. And this is where the calculations start to get a little bit overwhelming, because I need to take every single value, my 2, my 5, my 48, my 49, every single value, subtract 47.64, and square it, because my goal is to add all of those up together. So this is what my work looks like. I'm going to take that first value, subtracted by my mean. I'm going to square that, so it always turns out to be a positive number, and I end up with 2083.01. Then I'm going to do the same thing with that 5. I'm going to take my 5 minus my mean. I'm going to square all that junk, and I'm going to get my value. I need to do that for every single value in my data set, which is a lot. Whew! All of that stuff. Which is why, if you have access to Excel or something like that, just use it. But if you have to do this pencil paper, this is kind of how you do it. So we take each value in the data set, subtracted by the mean, and square it. Now, all of those numbers that we just gathered, we need to add those together. That is our summation. So we've already figured out the individual little chunks. Now we are adding all of that together as step number 4. And we come up with a little over 5,000 for that value. So we have the top part of that fraction. The bottom part is I'm going to take the number of values in my data set minus 1. So I have 11 values minus 1 is 10. So I'm going to take my summation divided by 10, which gives me 502.46. And my last step is to take the square root of all of that stuff. So I come up with a standard deviation of 22.42. Okay. And that is our sample standard deviation. Next, for our population standard deviation, the process is extremely similar. The only thing that we're really changing is that bottom piece. Instead of subtracting by 1 for our total data values, we're just taking the total data value. So the process is exactly the same. The symbols look weird. So the mu over here is still our mean. That x sub I is still each value minus our mean squared, summed up, divided by the total number of values in our data set. So just like we did before, we're going to calculate the mean, same old thing. I'm going to take each value, I'm going to subtract it by our mean and square it. I'm going to sum up all of those, and then I'm going to divide the summation by the number of values in the data set. So not 10 this time, but 11. And that comes up with our population standard deviation, because this is assuming we have every single value in a population. So like in our M&Ms, if we were able to collect every single M&M, we would be able to do population versus sample. The last thing we're going to talk about is taking these statistical ideas and how do we show them on a graph? How can we show the distribution of the frequency? So we're kind of almost combining this probability idea with statistic idea in order to come up with a way to show that and potentially get a little bit more use out of seeing that information really, really quickly. So let's say that we design an experiment where we are tossing a coin 3 times. And we are going to record how many times each event happens. So the variable x is saying if I throw heads 3 times, that variable is going to be 1 for heads, heads, heads. So let's say we take a bunch of data. We're flipping a lot of coins. Our thumbs are getting a little bit tired from the work that we've been doing. And so we have the outcomes of the toss that we could come up with, and we physically flip 3 times. We get heads, heads, heads. We get heads, heads, tails twice. Heads, tails, heads twice, and on and on and on. So the x value we are recording, how many times did we physically get that outcome? So with all of the values that we got, we never had tails, tails, tails. So we're going to try to change this into a frequency graph called a histogram so we can see what's going on there. So x equals 1 when we only see that occur 1 time within our actual work. So the way we're going to do this in Sheets in Excel, will kind of do this for us, is instead of graphing the outcome of heads, 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 tails on our graph, which would look really, really weird, we're going to do it against the probability that that thing is actually going to happen. So the probability for tails, tails, tails is 1/8. The probability for those 3 to happen is 3/8, 3/8, and then another 1/8. So the graph that I'm creating is not flip type versus how many times we get that. It's probability versus how many times do we get that. So the way we're going to graph that is for every time I didn't get anything, so I didn't get that tails, 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 1 out of 8 times, we plop that on our histogram. Same thing for 3 out of 8 for that specific flip. And same thing for those last 2 flips. So notice we get this nice little distribution of our flips showing that it looks like if I were to flip this again, it's most likely going to be one of those 2 3/8 problems. So one of the flips that we had happen twice. It's a little bit more rare not to get any, and it's a little bit more rare to get the heads, heads, heads apparently from what we're getting. So it's just showing how frequent is that thing actually happening. So how this might be useful is if we are creating a histogram for trying to figure out if there's going to be some open seats on the plane. So let's say you guys are flying to, I don't know, you're flying to Alaska, something like that, and your buddy is trying to hop on that plane with you. So if this is a data set of open seats 1 week before departure, you can kind of get an idea of the probability that a seat is going to be open. So if my buddy wants to tag along with us, it looks like we've got 0.03% chance of having 1 open seat there. If I have 12 people that want to jump in late and hang out with us, there's a really, really low possibility that that's going to happen. So it looks like the biggest frequency of open seats is going to be 5. So we're going close to 0.12% of the time. Now notice how if we were to add all of these up, it doesn't actually add up to 100%. And what that probably represents is that 0 mark is probably the rest of that. So we have a huge value where there are no open seats 1 week before departure. So this is going to help us look at our M&M activity and kind of figure out what is the most likely, kind of what bin does our data fall into